Now, my today's topic is the diaphragm wall, sessions for design and engineering. It will be presented by myself along with Ms. Anu James, my research scholar. Only the introductory part will be taken by myself, and the remaining part Anu will handle. So this is content. We would like to explain what is deep excavation, the introduction on diaphragm walls, the construction procedure of the diaphragm wall, load calculations, methods of analysis, modeling requirements, design of components, case study on trench collapse, and conclusions. These are the portions included in the presentation. Now, coming to the deep excavation, first of all, we can see what is an earth retention system. It is a system used for resisting lateral earth pressure, something which is used for resisting the lateral pressure from soil, and that is what is called a earth retention system. It need not be a permanent structure. It can be temporary also. If it is acting as a permanent structure, we can enclose an area and we can do some construction work in it. And if it is a temporary one, after our purpose, this system can be removed. And the application of the retention systems are that is for excavation shoring, that is to protect the sites, of the excavation, and the landslide mitigation, and that is very common. The rainy season is common in Kerala, in hilly areas. There we can use to prevent this landslide effectively. And again, as a permanent retaining wall, its behavior is almost same as that of retaining wall. So as a permanent retaining wall also it can be used. And why we want to apply this retention system? What is the necessity of this retention system? Is at present in urban areas we know that the cost of land is not only the cost of land. It is very difficult to get some area. Though we are in need of it and we are willing to pay for that, we will not get it. That much scarcity is there in land in urban areas. And with the available area, if you want to do some constructions above the ground level, some limitations are there. Depending upon the area only, we can increase the height of the building. So the only solution is to go underground. And if we are utilizing the underground spaces effectively, we can serve our purpose. So there is the importance of this deep excavations. 2 or 3 or even up to 50 meters below the ground level, excavations are made. So if we are not protecting the sites properly, it is sure that it will fail. So it is carried out in congested areas due to the underground space, usable space. And because of this deep excavations, the natural slope, the natural equilibrium of the soil will be disturbed. So we have to find some solutions to reinstate that equilibrium. There also, and to reinstate that, we have to do some construction. First, some structure to retain the earth properly, how to be constructed, and accordingly only we can retain the stability of the soil. So, to regain the equilibrium, the lateral support systems are used. So this shows an earth retention systems, and these are the structures which are usually adopted for deep excavation to protect the soil. That is, one is the sheet pile walls, secant pile walls, soldier pile walls, and diaphragm walls. These four structures are used to protect the sites. When deep excavations are carried out, we can protect the site by adopting one of these 4 structures. And regarding sheet pile wall, this shows a sheet pile wall retention system. The sheet piles, this is the shape, just like a trapezium, there is a shape, and at this end, it is connected with another trapezium type steel plates. And now this is the total width. We can say that this is the total width of the wall. And this is half one and this is another one. Similarly, the plates are connected. And then this on one side of this plate, the earth will be there and the earth will be protected. So this shows the retention system or the deep excavation, the protection of the sides with the help of sheet piles. And the another method is a soldier pile wall. Soldier pile wall consists of a number of load steel sections, usually edge sections, and in between the edge sections, we are constructing some concrete wall, reinforced concrete walls. So, or this reinforced concrete wall panel is inserted in between these two edge sections. Likewise, for any length, we can do the construction. And this type of construction is called a soldier pile wall. Then the third one is a secant pile wall. In secant pile wall, also at a constant interval, at a particular interval, we are first of all we are trying this piles. The piles are driven. The piles are driven at a particular spacing. And in between two piles, concreting is done, just like the circular or some other shape, we can do concreting. And then it will protect the soil. And this type of construction is called a secant pile wall, because these are the piles. This is also of the shape of a pile. Then the fourth one is diaphragm wall. And in diaphragm wall, this is a diaphragm wall which is constructed in Ernakulam. And this shows the diaphragm wall. It is a reinforced concrete panels. Reinforced concrete panels placed one after another. It is constructed. This is one panel, this is second panel, third panel, like that. It is constructed and joined. This is the joint. This joint is properly made. So this is the diaphragm wall. And these are the earth retention systems. And of these diaphragm walls, the diaphragm wall construction is widely adopted. This is the one construction site of a diaphragm wall. So this diaphragm wall is an embedded wall made with a reinforced concrete. And for the construction of this diaphragm wall, we are using the slurry trench techniques. I will explain what is slurry trench technique. And it is used for, the application is used for either as a retention system or as a load bearing member. This itself can be used as a load bearing wall, or again, it can be used for retaining earth. And the usual thickness, the thickness is varying from 600 millimeter to 1200 millimeters. And the depth it may go even up to 50 meters from the ground level. Up to 50 meters it will go. That's a very deep excavation. And because of these reasons, we have to be careful about the structural rigidity, the rigidity of the structure, the impermeability, and the durability. And if we are adopting diaphragm walls to go even up to 50 meters, the rigidity, impermeability, and durability is good. And that much advantage is there only for this diaphragm walls. So that is the reason why we are using diaphragm. Commonly, nowadays we are using diaphragm wall as the earth retention system. These are the, so many applications are there for this diaphragm wall. The one application is cut-off provision to support deep excavation. To support the deep excavation, as a cut-off provision, we can use this. And it is impermeable cut-off structure for hydraulic structures. For hydraulic structures also for as an impermeable cut-off, we can use this diaphragm wall. And again, for underground structures like a traffic underpass and underground tunnels, we can use this diaphragm walls. And again, it's a form of foundation. And these are the applications of the diaphragm walls. And there are various types of diaphragm walls according to the materials. You can say that there is a reinforced concrete diaphragm wall, or concrete diaphragm wall with the precast panels, or pre-tensioned diaphragm wall. Like that, according to the materials, we can classify the diaphragm walls as reinforced concrete diaphragm walls, precast panel diaphragm walls, post-tensioned diaphragm walls, etc. Then, according to the type of structure, we can say that there is a cantilever diaphragm wall, a braced diaphragm wall, and anchored diaphragm wall. This is according to structure. And this is one classification. This is according to the material. These are the types of or classification of diaphragm walls. Now we can see how to do the construction of diaphragm wall. And for the construction of the diaphragm walls, it is constructed panel wise. This is one panel, second panel, third panel, etc. So this one, the panel number 1 is made first, then the second panel is made. Then panel number 3, then panel number 4, like say panel number 1, 2, 3, 4. Panel wise, it is constructed. And with the help of mechanical grabs. These mechanical grabs are suspended from cranes, and with the help of that, we can remove the soil. And to protect the side, the bentonite fluids are used. After the soil is removed for one panel, then we are inserting the reinforcement cage. Then after inserting the reinforcement cage, the bentonite fluid already pumped in to protect the side of fluid quantity is pumped. The help of a stoppant. And similarly for the second panel also is considered. Then for the third panel, while constructing third panel, this stoppant can be removed. Similarly, the stoppant after the completion of one panel, we can remove the trench process used for construction of the diaphragm wall. First of all, the oil. From here, I'm depending upon the panel moving. While is pumped in, because of the slurry and the sides, it's a chemical solution. And after removing the soil and it is filled with the reinforcement cage already prepared outside can be inserted with the help of a crane. The reinforcement cage is inserted. Now there is a reinforcement cage with the slurry. Then what we are doing is we are removing the slurry. At the same time, the fluid quantity is pumped in. The fluid quantity is pumped in and the slurry is pumped out. Now this is the completed diaphragm wall with the reinforcement cage, etc. We can see. So this is the process for the construction of a diaphragm wall. And this shows some figures of the diaphragm wall. This is a reinforcement cage which is made on the ground, and with the help of a crane, is slowly lifting and keeping it in vertical position, excited in vertical position. And on the top of this is a trench. This is one panel. Here the trench is made. To this trench, we are inserting gradually or slowly. We are inserting the reinforcement cage. And this is the reinforcement cage that is constructed at the corners. At the corners, if there's a 90-degree turning is there. This is the how to prepare the reinforcement cage for the corner. And this is the stoppant. The stoppant can be either as a pipe or with the help of a channel sections or angle sections, etc. We can construct. Construct this end stopper. Then after this is one panel. The quantity is over. Then we can, with the help of the crane, we can pull out this stoppant. And that is regarding the construction procedure. And now this deep excavation we cannot avoid nowadays because of the scarcity of land. We cannot avoid this deep excavation because we have to utilize the underground space only can be utilized at present, because on land the land is not available. So since we are utilizing the underground space effectively, we have to undertake some deep excavations. And if deep excavations are there, we have to protect the sites. And to protect the site, we have to construct diaphragm wall. So it is inevitable in the present scenario. And the construction is easy because of the availability of bentonite and the processing plants. Then if the construction work, or if we want to do the construction of the diaphragm wall at a particular site, near to that site, we can install a plant for bentonite. And the excavation machineries are also available. And we can select the machinery and the type of equipment, the grab width, the panels according to the panel size, the width of the grab we can select. Again, the cutting rate also, all those things we can select. So because of this, because of the availability of these things, nowadays the construction of the diaphragm walls are easy. At the same time, there are some challenges. The challenges are there. One is how to keep the verticality of the diaphragm wall. The verticality, only an error up to 1% is permitted. If the verticality is not beyond 1%, we have to correct it. So the verticality of the excavation, we have to keep it as 1%. And again, we can see that we are excavating the soil. For one panel, we are excavating soil. While excavating soil, the chances are there to face the boulders. Big boulders are there. Big or hard boulders are there. And we have to remove that. To remove those boulders, we have to adopt some mechanism. Either we have to cut it into pieces and then we can remove it, or we have to adopt some mechanisms to remove those obstructions. Again, this is the bentonite level, and we have to keep that bentonite level. The sedimentation of the bentonite, we have to avoid the sedimentation. If the sedimentation takes place, the purpose won't be served. The purpose of the bentonite is to keep intact the sides of the excavator portions intact. And for that, the bentonite should be uniform. Always it should be uniform. And we are not allowing the sedimentation. So sometimes, because of some reasons, sedimentation may take place. If sedimentation is there, the trench will collapse. So that also we have that. These are also the challenges. So we have to find proper mechanisms or measures to face these challenges. And while doing the design, some factors we have to consider, that grade wall support, the soil strength, fluid strength. These are the factors to be considered with regard to the trench and the design of the trench support. And these are the forces to be resisted. That is the air pressure, hydrostatic pressure, and if some other surcharges like moving vehicles or big buildings are there, and because of that also some horizontal pressure will be there, those things also have to be resisted. So while considering these factors, the design of the diaphragm wall is done by considering these factors, and these are the challenges to be faced. So we have to make some proper measures how to be developed or designed to overcome these challenges. Now, this is the introduction regarding the diaphragm wall. The remaining part will be taken by Srimati Anu James. She is my research scholar and now working as assistant professor in the Department of Civil Engineering of MA College of Engineering. She has completed her work and has submitted the thesis, and now she is waiting for the defense. So now I am passing the remaining to present the remaining portions to Srimati Anu James. Anu James, please.
Thank you, sir. Good afternoon, everyone. Now we can continue with the analysis and design of a diaphragm wall system. Sir, am I audible?
Yeah, you are audible. You are audible.
Okay, thank you, sir. We can continue with the analysis and design of the diaphragm wall system. So for any system analysis, Determination of load distribution is the first part. So these are the primary loads which we need to consider for analysis of a deep excavation system. First is the lateral pressure. Lateral pressures in terms of by the earth pressure from the adjacent soil mass due to underground waters, any surcharge loads acting, all these we consider for any geotechnical analysis, let it be a retaining wall or by foundations. So that's the primary load for a deep excavation diaphragm wall system also. Next part is the vertical loads. This mainly arises from the comparatively larger dimensions of a diaphragm wall. This mainly include the self-weight of the system, then the skin friction components between wall and soil mass, and any vertical force components from the support structures, including struts or inclined anchors. In the design of normal retaining walls, the skin friction components are generally ignored. But for diaphragm wall system, due to its larger ground interaction area, this skin friction components need not be ignored. So we need to consider the axial load from that part. Next is the compaction-induced pressure. So in conventional calculations, the lateral loads induced does not include the compaction-induced pressures. So when calculated accordingly, by ignoring the compaction-induced pressure, that may underestimate or result in a reduced value of lateral pressure in case the earth backfill is a compacted area. So compaction-induced pressures need to be considered if required. So Canadian Foundation Engineering Manual and Australian Standard for Earth Retaining Structures, that is AS 4678, these two standards provide enough information regarding how to calculate the compaction-induced pressures for a deep excavation. So to calculate or analyze these loads, different theoretical and empirical equations are available. Most popular being the Coulomb's equations and Rankine's equation. But the researchers have shown that these equations are not adequate for the actual stress distribution calculation of deep embedded structures such as diaphragm walls, especially for calculating the load distributions and bending moment criteria for flexible embedded structures. Next, the commonly used empirical methods is the PEC's apparent earth pressure diagrams. This is the most popular and very widely used method for calculating the lateral loads. These are derived from studying a significant number of excavation case histories, and different expressions are given for different soil conditions. However, researchers show that these equations are not suitable for determining the design loads of rigid diaphragm walls. For flexible structures like sheet pile walls, computations using these equations reasonably agree with the field measurements. But these equations can be used for the preliminary analysis regarding the strut load calculations, that's the forces developing on the lateral support systems of the diaphragm wall, but not suitable for determining other design forces such as bending moments, axial forces, or shear forces. These are different standards and advisory documents which we can use for the analysis of a diaphragm wall and other deep embedded systems. So first is the Indian standard IS 9556, which is a code of practice for design and construction of diaphragm walls. This code is mainly about different construction methodologies and material characterizations. This does not provide enough information on analysis specifications and other reinforcement requirements. On the other hand, the European counterpart, that's the BS EN 1538, execution of special geotechnical works, diaphragm walls. This code provides more information on specific specific reinforcement requirements on diaphragm walls than our Indian standard. The other codes, third one is the Eurocode 7, the geotechnical code. Fourth, Australian code for earth retaining structures, then British code for retaining structures, and Canadian Foundation Engineering Manual. All these standards provide more information which are specific for deep embedded systems and diaphragm walls regarding different limit state conditions required, different safety coefficients required, and different reinforcement detailing specifications which are specifically stated for diaphragm wall system. So for the analysis of deep excavations, there are certain parameters which we need to consider during the planning stage itself, that include any possible basal instability in terms of basal heave or piping, then soil structure interaction between the concrete wall and the surrounding soil, provisions for unplanned excavations which can add to the stability of excavations. So in general, we need to consider all the aspects of the following conditions, that is different soil properties and groundwater conditions, loading conditions which may occur, including different types of loads that can act on the system, geometry of the excavation as well as the geometry of the wall and the adjacent locations, importance of the area. Similarly, how the proximity with the adjacent buildings, etc., we need to consider. And also different limit state conditions and the associated safety factors that have to be applied during the process of analysis. These are some of the failure modes that can occur for during a diaphragm wall analysis that we need to consider. First one is a loss of equilibrium to the structure, either by the rotation or translation movement of the wall. Then by lack of vertical equilibrium, if we underestimate or any miscalculations about the axial forces that can act on the system. The failure of different supporting structural elements, such as an inclined angle or strut or even the wall element. And similarly, the connections between these different elements, the supporting elements such as struts, vails, etc., are connected to each other. If the connections are improper, it may lead to the structural collapse of the entire system. This combined failure of the systems. Then we need to check the wall deflections and ground movements which are induced by the excavation process, and seepage through or beneath the wall, how the hydraulic failure or basal heave possibilities for these factors. All these are different failure modes which we need to consider. This is an illustration of basal heave and hydraulic failure system. The first image shows the possible basal heave. If the base heave of the excavation is more than the permissible limits, it will result in the yielding of the lateral support, thereby resulting in the failure of the system. The next image shows a possible hydraulic heave. This shows the formation of a flow channel leading to the collapse of the system. There's initiation of the flow channel leading to erosion and formation of the flow channel and ultimate collapse. So these conditions need to be monitored at the planning stage of an excavation. So to assist assist in forecasting these different failure modes or to determine the excavation induced behaviors, several sensing equipments are installed on a diaphragm wall system, such as inclinometers for field deformation measurements, and transducers for measuring the pore water dissipation, etc. This is an image showing a reinforcement cage which is installed with a pore water pressure transducer. So these inclinometers can give the deformations directly. And the strain gauges can be used, strain gauge readings can be used to depict the bending moments developing on the system. So such sensing devices are being installed on the reinforcement cage so as to determine the excavation-induced deformations and also to check on various failure modes. So from load analysis of any deep excavation system, either supported by a diaphragm wall or by any other sort of retaining structures, these are the different outputs we seek, like the deformation of the wall and ground, or other forces which are developing on the system, such as bending moments, axial forces on the wall, shear forces, and the forces developing on the supporting structures. To analyze these, different classical, empirical, and numerical methods are currently available. So as the classical method, we can adopt limit equilibrium approach. This is the simplest and quickest method, but this is not feasible for a rigid, deep embedded diaphragm wall system. This can be utilized only to compute excavation deformation, excavation-induced properties of a cantilevered or a singly propped wall. And this cannot integrate soil structure interaction characteristics, and also this cannot calculate excavation-induced deformations. The next popular method is the subgrade reaction modulus method, which is based on the concepts of beam on elastic foundation. In this method, the retaining soil and also the lateral supports are modeled as springs with equivalent stiffness. For this method to give reliable results, the input of the subgrade modulus must be precise. Next is the widely used method, finite element method. Different softwares are available for the analysis of deep embedded systems using finite element analysis, such as Plaxis, Geo5, etc. All these can be used to simulate any proposed deep excavation problem. So the advantage of finite element method over other methods is the different modeling possibilities. Nonlinear field conditions. It is very difficult and time consuming to model with using other methods, can be easily done using a finite element software. Staged excavation issues, dewatering characteristics, and soil structure interactions all can be modeled using a finite element software. 2D finite element softwares and 3-dimensional softwares are currently available. You can choose any of those. Even though different modeling techniques, including finite element method, can give us reliable results, there are certain requirements. For the results to be reliable, the modeling should be precise and appropriate with different field conditions, actual field conditions. So the different parametric values which we input to a software or to the other expressions, this value should be precise so that the results of our numerical modeling can be exact with the actual field measurements. So we should consider certain factors, including are all the modeling parameters available to us. In various finite element software, different soil models are available which we can choose from. So in those different inputs are required. So we need to check whether all these parameters are available to us, whether the present stress condition is known, or whether we need to estimate them or assume them, how to model the dewatering conditions. Different dewatering methods are available. So we should model the method we are using accurately so that at each excavation and construction stage, the lateral loads that we are computing is same as that of the actual lateral load conditions occurring at site. whether we should consider the corner effects and consolidation effects depending on the nature of the soil. All these are to be considered for a numerical modeling of the system. So now we can concentrate on the requirements of the finite element analysis of a deep excavation system. First is the different model properties. So boundary dimensions should be clearly specified while we simulate a deep excavation model. The boundary extent should be such that it should not interact or cut off the influence zones or different corner properties. It is always better to conduct a mesh convergence analysis so that we can know the variations in the results with different mesh sizes, and we should choose the mesh dimensions which does not cause much variations with further change in the mesh dimension. Similarly, the boundary conditions should be exact as the actual field conditions. Same is the case with soil model. The soil models we choose should be the actual mathematical representation of the field conditions. There are different soil models available. We can choose according to the complexity of the project we are handling. So out of those soil models with simple elastic considerations are easier one, but that may not be able to accurately represent the field conditions. However, many are still choosing the simpler soil models, either due to convenience or due to the unavailability of many number of parameters or insufficient data which we need to input for complex soil models. And accurate excavation dimensions and excavation sequence should be given. During any particular excavation stage, the actual unsupported embedded depth will be more than the predetermined floor height to facilitate the strut insulation. That should be clearly specified at the input stage or simulation of the model. Next is the geotechnical considerations. This includes the soil properties and the groundwater characteristics. While we consider the soil properties, proper judgment should be given regarding the nature of the soil. Drained and undrained conditions should be clearly specified. The stiffness of the soil should be properly given, and this in terms of the modulus of, we are giving it in terms of the modulus of elasticity, that should be proper. Then cohesive and non-cohesive nature of the soil should be considered by selecting the soil model. For cohesive soils, the excavation deformations may depend on properties such as creep, consolidation, etc. So we should consider these factors while we simulate the soil model. Next is the interface creation. This is to model the soil structure interaction. So without creating an interface, if you are modeling without an interface, it is like the soil and the wall is like tied up. There won't be any relative movement is permitted between those. While we provide an interface between the soil and wall, a knot pair is created in the model. So among this knot pair, one node belongs to the soil part and other to the concrete part. And all the relative movements are distributed in this interface area. So the properties across this interface area are simulated with our inter value. If that that input value is 1, the properties at the interface area is same as that of the soil mass. And if the value is less than 1, the properties of the interface area is correspondingly reduced relative to the properties of the strength of the soil mass. adjacent to that interface area. So characteristics of other structural forms such as wall elements, struts, center posts, etc. All for all these elements, the properties we are giving as input values should be appropriate for the actual materials. So we also need to consider the corner effects and how to model the panel joints, etc. The next parameter is the locations of the lateral support system, horizontal and vertical spacings of the support system, and also the installation angle. This table shows a feasible system of excavation and embedded depth combination with possible locations of lateral support for an idealized rectangular excavation system. So like this, it is always better to conduct a parametric analysis with these input factors, with these different properties, so that for any field conditions, we can compute the optimal values. Due to the extreme dependency of a numerical analysis on its input parameters, it is always recommended to have a material characterization of the different factors by conducting a back analysis with the field measured values. So that we need to have a better database of excavation case histories. So if such case histories or now prior data is not available, we can use the field measurements from the initial excavation stages to check our model accuracy and continue with further excavation. Now we can move on to the different components of a diaphragm wall system. We can categorize them as retaining system and strut system. The retaining system include different reinforced concrete components, and strut system include different structural components, structural steel components. So in the retaining system, it includes the main diaphragm wall and guide wall and the capping beam. The guide wall provides support and alignment to the, it guides the alignment of the diaphragm wall and also supports the excavation equipments. The different strut system, different components of the strut system includes the horizontal struts as shown in both directions. Then vails, which is the connecting member between strut and the diaphragm wall. Then braces and the vertical center post. This is a system model of a diaphragm wall from literature. The diaphragm wall and the supporting elements are modeled. Here the different connections such as strut and vail connections and strut and center post connections are given as hinges to facilitate the bending moment criteria and the bolted connections between this center post and horizontal strut. Boundary conditions are provided as per the proposed field conditions. This is an example of the simple modeling of a diaphragm wall system. These are the national standards which we can use for the design of reinforced concrete components. First one is IS 9556, Indian Code for Diaphragm Wall, and next is the Concrete Design Code IS 456. And the problem with these codes is that it does not provide information specific to a deep embedded system. And compared to these codes, the British code, it's 1538, it provides more information specific to diaphragm wall or deep embedded systems. The other two documents, there's a manual for detailing of reinforced concrete structures to Euro Code 2 and general guidelines for design and construction of concrete diaphragm walls. These two standards provide detailed information specific to diaphragm wall reinforcement detailing. So this is a diagram from BSEN 1538. It is a general layout of the diaphragm wall reinforcement. It's a general layout on how to detail the reinforcement of a particular diaphragm wall panel. These are certain reinforcement specifications assimilated from the above mentioned standards, such as minimum rebar numbers on each face, minimum diameter of the reinforcement bars, minimum clear spacing at different tremie positions when we provide the bentonite slurry, and clear distances between reinforcement adjacent reinforcement cages and reinforcement cage and the panel joint, thickness of the reinforced concrete at panel joints, etc. So these are obtained from basically from the third, fourth, and fifth standards. So this is the reinforcement detailing diagram for a diaphragm wall panel. The primary requirements include vertical reinforcement, which is arranged to be arranged in both phases, and horizontal reinforcement in terms of stirrups, links, etc. And suspension lifting bars are to be provided. Wheel spacers are to be provided at sufficient intervals. Special chairs are provided at specific intervals to keep the reinforcement alignment. This is a simple diagram of a reinforcement cage of a diaphragm wall panel. And this is the suspension hooks. It's a general layout of reinforcement detailing for crown beam and guide wall. Different layouts are possible according to the load considerations. This is the simplest general layout, guide wall reinforcement, and this is the crown beam reinforcement. These are some of the detailing layouts provided in the detailing manual to Eurocode. This portrays a diaphragm wall beam bonding and diaphragm wall slab bonding. So a few more reinforcement layouts are available in these standards according to the different requirements of connections between the diaphragm wall and the structure with which the diaphragm wall is going to support. Next, we can move on to the different components of a strut system. The design of the strut system component should conform with the IS 800-2007. So different components include the horizontal struts, then whale elements, braces, and center post. Horizontal struts are the elements which provide the lateral support to the retaining system. These are the horizontal struts. This provides a plan of the retaining system, and these horizontal struts provide the lateral support for the system. This is generally a compression member, but considering the self-weight and any possible live loads acting on the system, you can also consider design as a member with bending and axial loads. If required, seasonal temperature variation should also be considered. Whales are the element. This whale element is the component which transfer the lateral load from the retaining system to the strut. So this can be designed as a beam element with strut connections as hinges. Braces are the elements which is used to reduce the whale span. So during the construction or planning stage, if the distance between or spacing of two horizontal struts is more than the permissible limits, or by if adding another strut will result in too narrow spacing, then braces can be adopted. The last element is the center post. This is the component which ultimately carry the entire load of the retaining system. Normally, structural steel edge sections are used as a center post section. This diagram shows an illustration of a structural collapse of an excavation system due to the upward movement of the center post. This happens due to the large base heap. The upward movement causes the bending of the center post, which results in yielding and failure of the strut element, and which result to the ultimate failure, the inward failure of the excavation. These are some of the failure cases of diaphragm wall systems from literature. In these two cases, according to the literature shown, the designers overestimated the strength of the wall. And due to unexpected geotechnical conditions, it's resulted in the failure of the structural components, supporting components, which resulted in the ultimate failure of the system. So the image C shows the failure of an excavation system due to the poor design of wall, strut, and veil connection. The connection between the supporting elements were not proper, so that it could not carry the lateral loads efficiently, resulted in the failure of the system. Image D shows a failure system where the lower strut was not installed in time. Then the excavated depth, which was unsupported, the lower area was unsupported, and the unsupported depth was far more than designed, and larger standing time of that much unsupported length for more than permissible time resulted in the failure of the system. So we can consider a case study on a trench collapse of a cylindrical diaphragm wall system. This diaphragm wall collapse was reported in Taiwan, according to literature. It was a cylindrical diaphragm wall with a total diameter of 70 meters. Its depth was 90 meter depth. Total depth of the diaphragm wall was 90 meters. The wall thickness was 1.2 meter. There was a total of 32 panels. Out of this, 16 panels were having a width of 10 meters, and other 16 panels were having a width of 4 meters. Out of which, these 2 panels were for drainage purposes. And among these 2 panels, for this panel, after trench excavation and before reinforcement placement, a collapse was indicated by the ultrasonic sensing device. And this collapse obstructed the rebar installation. So upon investigation, it was found that an increase in pore water pressure was the major cause of the collapse initiation. And in addition to that, there was a deterioration in the quality of slurry, and there was a more unsupported standing time of the excavated trench. All these resulted in the collapse of the system. But this collapse was shown. It was detected by the ultrasonic device, sensing device placed before that trench was trench entirely collapsed. This was detected, and proper measures were taken, and this collapse was rectified, and rebar cages were installed, and further excavation was possible. and with timely actions, that entire collapse of the system did not happen. So the rebar proper rectifying measures were taken in this case. So concluding, we can say that the diaphragm walls are optimal earth retention system where we require more rigid structural support. As for example, in urban areas or where the soil properties are, soil strength is very low. In those areas, diaphragm walls are the optimal earth retention system choice. Different methodologies are available for the analysis of deep excavation systems. And finite element method, it's the most suitable method to to model these excavations, provided we can input most appropriate and precise values. We also discussed different components of a diaphragm wall system.